Good morning and welcome to lecture number 4 of module 3. So, in the last 3 series lecture on in module 3, what we have studied, we have seen minimization of 2 level Boolean functions or for 2 level circuits. So, what we have seen that given a Boolean function, so then how can we represent it using the minimum number of gates? Okay, that was the main idea, because more the number of gates or the gates with higher number of inputs means the more number of resources. So, given a Boolean function in the arbitrary form, so what we have to be, our main emphasis should be, the main emphasis should be that it can be represented or it can be implemented, rather say, in minimum number of gates, and also the gates being used should have as minimum number of inputs as possible. So, for that we want to minimize our Boolean functions in the 2 level. So, we actually represent our functions in terms of sum of product or product of sum forms, so which are nothing but a series of AND gates followed by OR gates, or series of OR gates followed by AND gates. So, the AND OR plane or AND OR plane kind of a thing. So, basically we see that most of all the Boolean functions can be represented by 2 level, can be represented in 2 levels, either in terms of AND gates first followed by OR gates, or the other way around. And we also by minimization, what we meant was that we have to implement so that the number of gates required are minimum as well as the number of inputs to the gates are minimum. So, we have done it basically in 2 steps. First we found out the prime implicants, and then we found out a subset of the prime implicants that would cover all the mean terms of the functions. So, basically you will see that already we have seen in the last 3 lectures that this problem is an exponential problem, or rather a doubly exponential problem in the number of inputs. So, finding out if you are using the Queen's or the tabular method of finding out the prime implicants, so if you have to first expand your function, Boolean function, in terms in a canonical, represented in canonical form. So, in the canonical form, that is all the terms are fully expanded. So, now by expanding, the number of mean terms can be the order of 2 to the power n in the worst case, where n is the number of inputs, and then again you have to do some kind of comparison, and then you have to eliminate out, you have to find out the compatible terms. Then what you do, then you have to find out the terms which are already included in some other term, and you have to keep on doing it, and in the end you find out the mean terms, the prime implicants for that function. So, that we have already seen by the tabular method. So, in the worst case, the input for the tabular method, that is, if that is representation of the function in a canonical form, may actually result in exponential number of elements in terms of the number of inputs. Okay, then we have found out that iterative consensus was another method of generating the prime implicants, in which we could avoid the what you say is this exponential problem of the tabular method, and you could easily get the prime implicants. Okay, but after you have found out the prime implicants, then you have to find out a subset of the prime implicants which can cover all the mean terms. Here we have seen a branch and bound algorithm, and then we have seen that if you are not using a lower bound to compute in the branch and bound algorithm, what do? You try to find out, you take a series of you take sum of the prime implicants, and then I try to find out whether there exists another solution by including some more prime implicants, and whether its cost will be increasing or decreasing, then a given predefined value. So, what do? We start with say that this basically we represent the whole solution space in terms of tree, and each node of the tree corresponds to taking or including or excluding some of the prime implicants, and then we try to find out if there is a better solution possible along a path from that node. Then we take that along a path, means each path in this branch and bound tree will actually correspond to some of the prime implicants being taken and some of them being dropped. So, if you find out whether through a path whether we can still get a better solution, if it is there, then you explore that path, otherwise you branch and bound back and try to explore other paths. Then you saw that if you try to explore the whole tree, it is going to be an exponential problem. So, we have given some heuristics where we have the lower bound computation heuristic. So, it will actually given a node, it will be a fast heuristic, and it will tell you whether there exists a better solution along that path. If there exists, then only you explore the path, otherwise you retract back and try exploring other paths. Okay, but here also the problem is exponential. If you forget about the heuristic part, it will be an exponential problem, because anyway you have to represent all the mean terms of the function, and then you have to find out which of the mean terms will be covered by your prime implicants. So, even if you include your heuristic, the problem if you do not even include the heuristic, so there the tree size will grow. That is because we know that selecting a subset of primes to cover a function is, in other words, a subset sum problem is actually an NP complete problem. So, overall the problem is an exponential problem. Only the heuristics is saving you by not allowing you, by helping you not to traverse some part of the tree. But in input space, you have to have the prime implicants as well as you have the mean terms. So, once you have the mean terms or any problem where you have the mean terms, then you can directly say that the number of mean terms in exponential case, I mean the worst case can be exponential in number, making the whole problem a exponential problem. So, the heuristics will help you to save some computation part, but actually it cannot minimize, turn it down from an exponential problem to a polynomial problem or something like that. Why? Because you have to enlist or you have to list the mean terms in picture. So, all the mean terms you have to list and then you have to find out which are the prime implicants which will cover it. So, whenever you have to talk about all the mean terms in case of the branch and bound, or you have to talk the mean terms when you are talking representation in canonical form is nothing but you represent the mean terms, that also when you are finding out the prime implicants by the tabular method. So, whenever you are bringing the picture of mean terms into picture, so your problem is becoming exponentially complex. So, actually finding out the minimum, what you can say, minimization of 2 level circuits or 2 level binary Boolean functions, but the techniques we discussed in the last 3 lectures, that is finding out the prime implicants and then selecting a subset cover using branch and bound algorithm, is actually an exponential problem. So, if the number of inputs of a function is say about hundreds or 200s, then you cannot use the techniques mentioned in the last 3 lecture series, is an infeasible way of handling the problem. So, what we are going to see in this lecture? In this lecture we will see heuristic minimization of 2 level circuits. In this case what we are going to do? We will be actually we will not start or at no point of time we will be talking about explicitly about the mean terms. We will have a what you call a Boolean function and then we will try to minimize it from that point. It will be somewhat similar to iterative consensus kind of a thing, where you will start with given any Boolean function in any format, we will not convert it into a canonical form, rather we will try to minimize from there itself. Okay. So, that is actually you are not expanding the terms. So, if you are not expanding the terms, then we are being saved from the computationally exponential problem, and also we will never explicitly talk about the mean terms that is being covered. So, we will land to a minimal problem, but again it will be will be heuristic, because at no point of time we will have an exact algorithm. So, it is totally in all even from the beginning, I mean in the last 3 lectures we actually computed the prime implicants. So, that part was an exact algorithm, I mean we never use a heuristic to compute the prime implicants, but here there will be no question of prime implicants, no question of mean terms. We will be given a Boolean function and we will try to minimize in some way, as we will be seeing in this lecture, and it will be a heuristic from the day one kind of a thing. So, there will be no exact algorithm involved in any part. So, your algorithm will be a very fast algorithm, but again the solution obtained may be an suboptimal one, or you will never get an optimum solution in most of the cases. What do we say? The solution will be a near optimal solution. Okay. That is the idea. So, whatever I told you, I discussed you, that is mentioned in the lecture. We have Boolean function minimization for 2 level implementation. The major problem is the potential very large number of mean terms and the prime implicants. So, mean terms and prime implicants. So, mean terms will be much more larger, as you know, from the prime implicants, but anyway in the worst case both of these prime implicants and mean terms can be very high in number, or you can say an exponential in number, making the whole problem a very difficult problem to solve. Okay. So, exact minimization procedure involve 2 basic steps: finding the prime implicants and determining a minimal subset. So, actually determining the prime implicants, if you use a tabular method, it will be exponential. Okay. And if you are using iterative consensus, at least at that part you are being saved from an exponential complexity, but when you are going to find out the minimal subset, this problem is going to be an exponential problem, because you have to enlist the mean terms. Okay. So, if you have about say 2 to the power n mean terms in the worst case, so I mean if the circuit has n inputs, in the worst case the order of the mean terms can be order of 2 to the power n, say for example where everything is 1 in this case. Okay. So, if you have a circuit with more than 15 inputs, so it will be solution space will be so high that it will be virtually impossible to do it using a computer, and or in other words the time taken will be extremely large. Okay. So, what we will go to cater this problem, heuristic method for Boolean function minimization has been proposed. So, which avoid computing all the primes and the mean terms to avoid the computational cost. So, what is the basic idea here? So, that is what we will be looking in this lecture. The basic idea is that we will given any kind of a Boolean function, we will not go to find out its prime implicants, nor will be try finding out its mean terms, rather we will try to minimize from there itself and see how much we can minimize. Okay. And that will be your result. So, obviously it is a good heuristic, because the time taken will be much less, but you may get a suboptimal solution. Okay. So, what is the idea? The idea is to successively modify a given initial cover of a function until some stopping criteria is met. The drawback is inability to guarantee the cheapest solution, okay, but careful choice of algorithms will provide solution very close to the optimal time in a very optimal results in a very reasonable time. So, what it is saying? So, we will be given an initial Boolean function, then what we will do? We will try to because that is actually a cover. So, given an initial Boolean function means it is represented in terms of some ands and ors, that is in say say it is some SOP form. So there will be some product terms which will be added. So basically they are nothing but they are actually covering your function. So given any Boolean function, it covers the function, that is very well known. Okay, now what you have to do, now again we actually, if you try to find out the prime implicance, then again the procedure is there, as we have already seen, as which are maybe an exponential case. But here we are not going to find out any mean terms, or we are not going to find out any number of prime implicants. Rather we will try to represent the function in different ways, so that the number of literals, total number of literals try to become minimized and smaller and smaller. We try to, in every subsequent step we will try to minimize the product terms and the number of literals in each of the product terms, so that the same function is represented, but the number of literals start becoming less, and we keep on doing it, so that there will be some stopping criteria. Say that if you have 100 literals for a function, we are very satisfied and we can stop. So 100 literals means, say about, we can have order of some about 100 inputs and some different product terms will be there. Also a stopping term can be some number of product terms. Some number of product terms means that number of AND gates. So what you can do, you can keep on heuristically minimize the function by actually removing one literal, putting another, and so that the function remains equivalent. And what is the stopping criteria? Say if you have 100 literals or about say 10 product terms, so that you can stop. That means you require 10 AND gates. So, and that is you can put some heuristic, that is again the stopping criteria is also a heuristic, that is given a bound on the number of literals, or on the bound of the on the bound on the number of product terms, that is the number of AND gates, and so forth. And finally, so you keep on minimizing your function. So if you reach a stage where you find a number of literals or number of the AND gates is equivalent to your stopping criteria, you stop and you produce the result. So here what is the interesting thing about this algorithm will be, the more the time you run, the chances that you are going to get better and better results. Because if you set a very lower bound on the number of the AND gates or the number of literals, then you have to execute the algorithm for a very large number of time, or a sufficiently large number of time, and then you can get a minimal representation. But if your stopping criteria is quite relaxed, like you get 300 literals or 100, 200 AND gates, so you can get the solution very fast, but in that case your solution will not be a very optimal one. Okay. So now in this lecture, actually the name of this algorithm call is Espresso. In this lecture we will discuss a simple version of this heuristic. Okay. So, till now we have been talking about exact algorithms and heuristics, and what is the advantages of heuristics or the disadvantages of heuristics. So, before we exactly go into this two-level minimization heuristic called Espresso, so let us see what are these heuristics based on, mainly for this logic minimization problem. So, heuristic based logic minimization are based on local search. So, we see what is the local search, because we have till now not defined what is the local search, which is a global search in terms of these heuristics. Okay. So, in this lecture we will give you a very quick overview of what are these heuristics are about and what do you mean by local search. So, what these algorithms will do? The algorithms start with an initial solution and try to find out a better solution by successively modifying what is called local search algorithms. So, the algorithms will start with the initial solutions. Initial solution means the initial cover. In this case, you are given a sum of product form of a Boolean function. So, obviously, it will cover all the mean terms. That is very well known. So, that is actually your initial solution, and try to find out a better solution by successively modifications. So, in this case, what you can do, as we will be seeing by examples, you try to modify some of the product terms, so that some of the product terms can be totally done away with. If you find out some redundant terms, you can be done away with. Then you can also minimize these two terms, like for example, if you have x, as I told you, x a plus x something like this is plus x bar a. If something is there, then it will be a into x plus x bar, that is equal to a dot 1, that is equal to a. So, this type of small minimizations you can do, so that your number of product terms or number of literals in the product terms will keep on decreasing. So, such type of modification, minimum is small modification you keep on doing. Okay, that is actually called successive modifications, and they are actually nothing but your called local search algorithms. So, after doing this modification, your functions should remain equivalent, and then you should compare if the number of literals are and the number of product terms are decreasing from the initial solution. If it is there, you keep it and then again try doing further more modification. This is actually called the local search. So, local search algorithms are very common in optimization domain and minimization also in the VLSI area. So, local search means what? You have given a solution, then say you are given a solution, you try to find out some solutions which are nearby. So, how do you find out solutions which are nearby? Just by tweaking some of the parameters. Then if you see that whether this neighborhood solution is better than the current solution, so you take this as the present solution and you keep on repeating it. Okay. So, in selecting a subset of prime problem, the search space consists of a subset of primes that covers all the mean terms of the Boolean function. So, if you consider that you are giving, so in this lecture we will not start with the case where the prime implicants are given to you, rather we will start from a canonical, rather we will start from a given function and we will try to minimize. But if you just take for example the previous lecture that we have been given some prime implicants, okay, which cover a function, and then you have to find out, then you have to say that how can you go for a local search in this. So, local search in this, you randomly take a subset of prime implicants which cover this, then what you do, then you tweak something, you remove one prime implicant, put another prime implicant, or you remove a subset of the prime implicants from the set and add another subset which will still cover the function. Okay, so, when I am saying that you remove some of the prime implicants and add some of the prime implicants, that is you are going from one solution space to another one solution to another solution, and both of them should cover your function. So, that is what is called the search space. So, search space is a subset of primes. Now, this is one solution, a subset of prime covering your function is a solution. Now, you exclude some of the primes, include some of the primes, this is actually another solution which is nearby. You go to that solution and see whether it covers your function, and also if the number of terms are less than the previous one. If it is the case, you take the new solution as the new solution as the current one, and you keep on repeating it till you get to your stopping criteria. Okay. So, a point in the search space is a subset of primes. Okay, the subset of primes which cover all the mean terms is a valid solution. Okay, now there is something called a valid solution, something called an invalid solution. Like if you take, like what is the solution space? Solution space are nothing but subset of primes. Okay, please remember that these 2 points I am saying are not relevant to today's lecture, they are relevant to the other previous 3 lectures, because there we had a subset of prime, there we had prime implicants, and we were trying to find out the minimum set of prime implicants which can cover the function. But in today's lecture we will not at all bring in prime implicants into consideration, but rather start working from the function in the current form. But as we are defining what is local search, so we are trying to correlate local search heuristic with the previous lectures. So, what is the if you are given in the corresponding to the last 3 lectures, if you are giving us given the prime implicants for a function, and if you want to find out a subset of prime implicants, you are not taking the branch and bound algorithm, you are directly going for a heuristic. So, in this case we can say that local search is a good heuristic. So, in this case what you do, you take an arbitrary set of prime implicants, that is a solution space. A subset of prime implicants is a solution space. Now, it can be valid or it can be invalid. So, if it is invalid means what? If it is invalid, that means it does not cover the function, and if it covers the function, then it is a valid solution. So, you take a subset of prime which is a valid solution. Now, what you do? Now, you remove some of the prime implicants, add some more prime implicants into the set. Now, it will become another solution. Now, you have to find out if it is a valid solution, it is fine, and if it is an invalid solution, you discard it. If it is a valid solution, you find out whether the number of mean terms and the product terms is less than the previous solution. If it is the case, the present solution becomes your this current solution becomes the new solution, and you keep on iterating it and you keep on doing it till you get a solution which has the number of mean terms and the number of product terms, the number of literals and number of the product terms as per your desire. So, more you do refinement, the better and better solution you give, and more time you take. Okay. So, this is actually called the local search kind of a thing. So, the subset which covers all the mean terms is a valid solution, and the ones do not cover mean terms is not a valid solution. The set of points in the search space that are valid solutions are so called the feasible region. The complement is the infeasible region. So, there will be different subsets of prime implicants possible, that is a power set. When the subsets which actually cover the mean terms is the valid set, and the others one is the invalid set. Now, you have to find out, actually you have to keep on searching within the valid set, and you have to find out the solution whose cost is the minimal. We should not call it minimum, which is the minimal, and finding the minimal better and if you are going towards the optimality will take more time. So, if you are giving more time, the better and better solution you are going to find. Okay. The local search relies on distance between 2 points in the search space. Like what is a point in the search space? That is a valid solution. Okay. Now, in case of selecting a primes, the problem distance between 2 points is the number of mean terms that are covered by one subset of prime, but not in the second, and vice versa. So, I will tell you what do you mean by a distance. So, in this case, if you say that what were the points in the solution space, a subset of prime. Okay, now you have to define a distance. Distance can be anything. One parameter of distance can be given the number of say this is a solution space, so it contains some amount of prime implicants. Okay, so if you can say that the number of prime implicants or the number of literals in the prime implicants is the measure of distance. So, if there are 2 points, so if it has say 100 literals and this also has say 100 literals, so you can say that the distance is equal. But if you say that this has 100 literals and this has 50 literals, then you can say the distance is 50. So, you can also have a complex distance function, like you can say the number of prime implicants, that is the number of product terms in this case, and the number of literals. If you add that or make a formula, that is the measure of a distance. So, if it is 100 literals and say 20 prime implicants, and this is say that 50 implicants and 50 literals and say around 15 prime implicance. So, this will correspond to 65 and this is corresponding to 120. So, you can find out the distance. So, in this case this is actually this is the distance measure if you are talking only about the valid solution points. But if you are talking about the general case, so you can have the distance measure in a very similar way. You can say that in a subset of prime terms, distance between 2 points can be the number of mean terms that is covered by a subset of primes. So, actually here in the second point it is stating that we are not considering at all the valid points now. So, some of the solution space that is subset of primes may not cover all the mean terms and some of them may cover all the mean terms. So, I mean the distance measure can be the number of mean terms that is being covered by the prime implicance. So, if here actually that is actually cardinality of the symmetric difference of the two sets. So, there can be various distance measures. So, if you are considering all points and the number of mean terms covered by the subset of prime implicance can be a distance measure. Or now if you are considering only about the valid solution, so you can say that the number of prime implicants in the set plus the number of literals in the set becomes your distance. So, the difference between 2 points can be easily find out. Okay. So, different problems may have different definitions of distance and also it is possible to define different distances for the same problem. So, that is what I told you. So, number of literals can be one distance measure, number of literals plus number of prime implicants can be measure, or also only the prime implicants can be a measure and so forth. So, okay, once the definition of distance is given, we can find out the neighborhood of a point P as the points which are some less distance k from this. That is what my idea is, that in local search what we do, we first have a solution, then we do not go to a solution which is very far. What we do is that we try to find out a periphery of the region whose distance is less than a threshold say k. Then we try to find out the nearby solutions to this point. Then we find out if there is any solution which is better than the present solution, that we make as that new solution as the present solution, and then we again try to make a neighboring part of it and try to find out which is the best solution among this, and we keep on doing this. So, if you can understand that if this is a very good solution, so sometimes you may reach up to this point. Okay, so why we actually go for a local search? Because if we too much change the distance, then you may not settle down to a good solution. You may always be oscillating. You may get a good solution, then you get a bad solution, and then again you get a good solution and so forth. So, that is what we do. We actually increase our movement of the points in the solution space or the search in the solution space in a very slow manner. That is why it is a local search. We first take a point, search in the nearby spaces and find out if there is a better solution there, and then we take it, then we again slowly move. It is not that we start from one point and quickly jump to another point and then again see what is the case and again come back. So, you may not converge in very quick, solution may not converge, you may keep on oscillating. Okay. So, we start from an initial random solution. The algorithm examines the neighborhood for a feasible point whose cost is less than the current point, as I told you. If it is found, it is assumed as the new start point and the process is repeated till you get a the better kind of a solution. So, now you are representing in a graph. So, let this be a function in terms of f of x. So, this is your actually this is your function and then in terms of a graph. So, you can say arbitrarily you can start off with this point. Okay, now what we will do? So, now you can find out the solution space nearby, the neighborhood. So, you can find out that this is the best solution in the nearby point. So, this will be your next solution. Now, what you do? So, say this was a random start point, then you find out that this was the next better solution, the random point. Then again according to this neighborhood you find out next solution, this solution 1, this solution 2. Then you find out the next best solution, then you again put a boundary around it, that is your again next neighborhood, and then you can find out this is the best solution. If you keep on doing it, and then you will find out that I am in this bottom, then wherever you go here or wherever you go, so finally you will reach here, then whether you go this side or go this side, the solution will not be a good solution. So, you can say that is my stopping criteria and you can find out the minimal one. So, in this case, if the for example, but this is actually you have to observe that this is a convex function. So, for example, if you are interested in the minimum of a convex function in the real variable as one shown in this figure, local search optimization consists of moving downward along the curve and guaranteed to find the solution with the minimum value. Okay, so, if your function which you are trying to minimize or you want to find the optimal point in it, if it is a convex part like this, then obviously local search or local heuristic is going to give you the optimum solution, that is guaranteed, because you first do this, then you find out the nearby, then you here, then you go here, and you have to keep on doing it for some amount of time. So, if you say that my stopping criteria is very good, very relaxed, then you can stop over here. You can find out that at this point I could have got a better solution, but I will stop here because my time is critical and I don't want to go about for more amount of time. And this is also a good solution by my terms of criteria. So, you can stop over here, but given a sufficiently amount of good time, the local search will actually bring you to the minimum point. Okay, but life is not always very simple, because generally a solution may not be as convex, may not be a convex like this. The solution space can be something like this. So in this case what can happen, that your solution may get stuck in something called a local minimum. That is, say you start with this point, then you keep on, then you make a point, you come here, then you make a point, you come here, then you make a point, you come here, then you come here, and then you find out that if I go this side my value will increase, if I go this side my value will increase. So this, it will appear that this is the best solution for me, I will stop. But actually this is not, because after rising, then actually after rising, this was the best solution, but if you can somehow throw away this best solution for the time being, then you can jump over this and then you can find the global minimum. This was a local minimum. So local searches actually will stuck in this type of local minimum points if your function is not a convex function. So in case of this 2-level Boolean minimization and all, so they are never as smooth function as this. So therefore our heuristics always get stuck in something called this local minimums, and generally we are not able to find out the global minimum, which is the optimal solution. So it is the most optimum solution. So we get stuck in the local minimals. So these are the optimal solutions. But there are some techniques which we will not discuss in the lecture. That is, sometimes what we do is that if you get a local minimum and you find out this is not, this is both way increasing, but still you have some computation time left as per your criteria. So we can give a jerk to this one, jerk to this point, so that it can overrun this one and you can just try to find out the global minimum. But that is very advanced stuff, which is an advanced stuff we are not discussing in this. But for the time being, just to understand that why search heuristics do not give a very good result, may not give an optimal result, because you may start, but if you start with this point as the first starting point, then obviously you will get the global minimum, which is the optimal solution. But if you start from here, then you may get stuck in the local minimum. So that may also happen. Therefore, we sometimes may or may not get the most optimum solution. Okay. So if the function is not convex, then the search may get stuck into a local minimum. So at this point you may not get the best solution possible. Once the local search reaches the local minimum point, it terminates, because it cannot see a better solution in the neighborhood. However, it takes a worse if it takes a worse solution compared to the local minimum, there is a chance that we may reach the global optimum. Okay. However, if it takes a worse solution compared to the local optimum, that means what? That is, you have to give a jump. That is, if you take a worse solution than the present one, that is, you are giving it a throw for some time, then you can cross this hump and you can reach the global minimum. But again, you have to again decide at what point you will go to this, you can take the worst solution compared to the good solution, and so that you can try the hump, because it is not very simple. Say if I do not know whether I am in local minimum or I do not know whether I am in global minimum. Say for example, if I am here, then I find out this is also a bad solution, this point will be a bad solution. But if you want to accept a bad solution or a worse solution than the present one, to try to cross the hump, then you can try to move the solution point, then you will land up here and you will find out that this was a better solution than this one. So your whole effort and time has been lost. So therefore, if you get a minimal solution, still you are trying to cross the hump by selecting a worse solution, it may not always be a fruitful result. So this is a very difficult decision to make, that when you have to take the local minimum, or when you have to forget about the local minimum, take a worse solution and try jumping about it. Okay. So in the first case we said that the solution is minimum or optimum, and in the second case we call this solution is minimal. So this is minimal or local optimal or something like that. So in most of the heuristics in case of circuits, we get the optimal solution, not the optimum solution. Okay. Okay. So one general interesting property of the solution in a local search algorithm is local optimality. A solution is local optimal if its neighborhood does not contain a solution of a lower cost. Okay. In order to guarantee local optimal, it is sufficient to use the stopping criteria where no cheaper solution exists in the neighborhood. So you can also think about there are different type of stopping criteria, as I told you. So one stopping criteria is that you define a neighborhood, and if there is no better solution in the neighborhood, then also you can stop. Okay. So that can be some of the ideas. But for the heuristics we will be generally using, we generally try for the local search only, because searching for the global optimum may be very difficult and time consuming. But sometimes we also try that, because if you have more computation time is given, then you can try of even crossing the humps. Okay. So we will just, these were some of the basic ideas of what you call the heuristics, local search, local optimum, global optimum, because in the first design part of this course, in the last 10 or 12 lectures, we have always discussing that this is an exact algorithm, this is an heuristic. Heuristics may give you optimal solutions, not the optimum solution. So why all this happens? So today we gave you just an overview. Okay. So now we will see how local search is applied to logic minimization. Then we will go for the algorithm Espresso. So okay, so local search based heuristic local search based logic optimization starts with a random subset of primes. Okay. So please do not confuse this with Espresso. Espresso algorithm in this case will not start with a prime implicant, that will rather start with a general given SOP formula and keep on minimizing using the local search. But this local search example we are giving on the example where prime implicants are there, that is previous 3 lectures series lectures which we have done. So, we are applying the local search to that results. Okay, we are not applying it to Espresso or the heuristics which we will be trying to, which will be looking today for what you say this logic minimization. Okay, so logic minimization heuristics, if you talk about Espresso, it does not take care anything about the prime implicance. It will directly take a SOP form and start minimizing. Okay, but this local search we are applying the logic minimization of the previous lectures, 3 lectures with prime implicance available. Okay, so so we initially start with a random subset of primes, which is a cover. So, what you can do? You can take a random subset of primes and find out if it is a valid solution. So, if it is a valid solution, then it should cover the function. Okay, and if it does not cover the function, then you can say the invalid solution and try for another random subset. Okay, the cost is the number of cubes. So, as I told you, cost, distance, whatever you can say, in this case is the number of cubes. It can also be the number of prime implicants. It can also be the number of literals. So, anything can be there. So, if 2 solutions have the same number of cubes, then the number of literals can be used as a secondary cost, as I told you. Okay. Okay, that the neighborhood of a solution is the subset of primes that are obtained to the solution by adding or removing exactly one literal to and from one of the cubes. I will tell you what does that mean. Okay, so that means if you have some number like x, y, z prime. Okay, so plus something is there. So what is another point, I mean, which is how do you find out another alternative solution? So in this case you say that I remove this. Okay, the neighborhood is found out by just remove this. The neighborhood of a solution is are obtained from the solution by adding or removing exactly one literal from one of the cubes. So, you take one of the cubes and remove at least one of the literals. A new cover is obtained is a valid solution, okay, and consider if it represents the same function. So, if you just remove this, then it may become a invalid function also. So, if it becomes an invalid function, then you have to throw away with it, but if it remains an invalid solution, then you can, I mean, think whether the cost, obviously cost has reduced because you have removed one literal. Okay, and then you can think that this can, that is what we are minimizing with. We start with a given set of prime implicants, then what you do? So, the cost here is the number of literals, okay, or the number of cubes that you can take. Now, what you do? You have to minimize. So, what you do? You remove one literal from one of the cubes. So, that is the next solution you can think. Okay, so, you are slowly moving in the solution space. So, as I told you, another way of finding out the solutions could have been another random subset of prime implicants which is valid, and you keep on doing it till you get the minimal number of prime implicants. That can also be one of the solution. One way of doing the local search. But now what we are doing here, we are trying a slightly different. So, in this case, we take a random subset of prime implicants, then we take one cube and remove at least one literal from this one. So, removing one literal means we are actually trying to get a minimum number of solutions. So, when you are randomly selecting the prime implicants, so your criteria should be, so initially say you have taken a subset which is having 10 prime implicants. So, now when you are selecting another set of prime implicants, obviously the number of literals or the number of prime implicants should be lower than the one in the current solution, if you are taking that approach. But in this slide which we are presenting, we are taking a slightly different approach. In this case, we are not taking another subset of random subset of prime implicants as the solution. Rather, what we are trying to do, from one of the cube we are removing one literal. So, what it does? It will actually modify the function. So, you have to just check whether it still covers the function or not. If it still covers the function and is equivalent, then it is fine. If it remains equivalent and still cover the function, that means you have removed one literal and you have reduced the cost. So, you have to keep on doing it till you are satisfied with the cost of the function. Okay. So, their new cover is also obtained is a valid solution, then only it has to be considered and it represents the same function. So, then it is considered, otherwise you have to again replace back this literal and try with some other. Okay, solution is the solutions with more number of cubes than the current solution are not considered. So, that we will see. I mean, obviously the cost increases. So, in this case the cost will decrease. So, if the cost increases, then obviously nowhere it will make any point. Okay, so I mean whatever I told you, it will be more easily illustrated if I give you an example. So, let us take this function. So, it is x, y, z prime, this one and this one. Okay. So, you can find out that they are nothing represent the initial cover. The cubic representation is as follows. So, we can see that these are all 0. So, it is represented over here. Now, if you take this 2, so you can see that it is nothing but x y prime, it is x prime y. So, it is x prime y, z and z prime. So, if you merge these two, you are going to get 0 1 dash. Okay, and then again if you merge this 2, so it is nothing but y z. So, it is 1 1 and it is x and x prime. So, it is this way. So, you can represent this function in this way very easily. 0 0 0 the answer is 1, 0 1 dash the answer is 1 and 1 1 1 the answer is 1. Okay. So, now we can represent it in a cubic fashion. So, what is the cubic fashion? The cubic fashion is simple, you represent a cube like this. So, this point will represent all zeros. So, this direction is z, this direction is x and this direction is y. Okay. Now, so this point is obviously 0 0 0. So, if you move in this direction, it is x is becoming 1, y and z are still 0. If you move in the top direction, the z point will be 1, others will be 0. If you move in this direction, obviously y point is become 1 and it says 0. So, what will be this point? In this point you can see that you have moved top. Okay, so we have moved top means z is becoming 1, you have moved in this direction. So, that means y has become 1, but still you are in this font, you have not gone in this font. So, x is 0. So, in this way you can make out this whole cube can be explained, and obviously in this point where everything is 1 1 1. So, the answer is 1 1 1 and it is the terminal point. Now, you see we represent the point 0 0 0. So, this is the initial cover. So, it is 0 0 0. Now, it is 0 1 dash, that means what it is 0 1 1 and 0 1 0. So, 0 1 1 is this point and 0 1 0 is this point. So, obviously, if I make this is this cover corresponds to 0 1 dash, and again obviously now you see that it is 1 1 1 and 0 1 1 this term. So, this is nothing but 0 1 1 and 1 0 1. So, these two terms if you combine, that is this one is nothing but 1, this one is your this thing. So, you can find out that So, you can easily see that this is what is going to be your which is going to look like something like this. Now, I will tell you what does it mean. Now, you can see that this is your initial cover. Okay, now, what our idea was that we have to try to remove some of the literals from some of the function and see still it works or not. So, if you look at this function, it is called x prime, y prime, z prime, if you just look at it. Okay, now, you can easily see that let me try to remove some function, remove some literal from this one. Okay, so, now, if I remove say literal this y prime, if I remove from this one. So, then what it is going to become? It will become x prime, nothing will be dash z prime, that is 0 dash 0. Okay, so, what does it corresponds to? It will correspond to these two terms. Okay. So, now, if I this one was 0 0 0. So, if I eliminate this one, so it will become something like this. So, obviously, by eliminating y prime from the first term makes it a valid solution, because it will still cover the function and no more new mean terms are anchored into this one. So, it still remains a valid solution, and then you can find out that this second term, that this one 0 1 dash will become a redundant cover and it can be removed. So, your function will become what? It will become x prime dash y prime plus the last term will be dash y z. This one will be your final function, because this middle term you can do away with. Now, you see, so how you can find out y is a valid solution? Because by removing y you can find out that this point will actually grow into this one. This was the initial point, so it is a valid solution because all the mean terms are covered and no extra term is covered. But say if I remove x prime, so if I remove x prime from this one, so it will what it will become? It will become dash 0 0. That means it is 0 0 0 and it is becoming 1 0 0. So, okay, so this is actually covering this two. So, this is actually dash 0 0. So, that is not, it does not at all remain a valid solution, because it will make a cover like this. So, it is an extra mean term which is covered, which is not actually not allowed in this case. So, this will, so removing x in this case will not keep it a valid solution. So, only the valid solution will be x prime, y prime, z prime. So, y if you remove, then it will remain a valid solution, and then this will becoming this one, and your terms become a better solution. So, what we have done? So, our initial solution was this one. You can find out that this may be this set of prime implicants. Okay. So, here in this case you started with the set of prime implicants. You may also not start with the set of prime implicants, you can directly start up with this function set also, that is also possible. Okay. So, in this case you find out the 3 primes, you started up with this one, then you actually start eliminating one literal from any of the terms. So, in this case I started, you can start with anything, you can start with x prime and then it from this one, and you find it does not become a valid solution, because it becomes this way. Then you start eliminating y prime. If you eliminate y prime, then your solution will be nothing but it will look like this. Okay, and then you can find out that this becomes a redundant stuff and it can be removed. So, this is a better solution than the previous one, and you keep on doing it till you get your desired solution, or what? Or you can fix a stopping criteria. Like if you think that in this case the solution is 1, 2, 3, 4, 4 literals are there, 2 terms are there. So, if you think that 4 literals and 2 terms are there is very fine for you, you can stop here. Otherwise, you can start eliminating z from here and see something like this. You start eliminating x square from x prime from this and see what happens, and keep on doing it. And you have to do it till the solution should be better, as well as, and in the same case you should be having a valid solution. So, what do you mean by valid solution? That is, it should cover exactly the same mean terms which was being covered by the initial solution. Okay. So, let us now, that is what I told you, you remove y from this one which is leading to this one. It may be noted that we can do so because it covers mean term this and this which are to be covered in the function under question, and it is not in any way covering any additional mean terms. After removing the returning y from the cube, we get the solution in figure C, that is what we have shown. Okay. And then so we can remove this redundant cover, and this is your actually optimum solution. In this case it is optimum, okay, but in a general speaking case you have to keep on doing this till you get the desired solution or your time is over. Okay. So, now we will see the same thing for a two output function, same thing will apply to a two output function. Okay. So, I mean you can think that this is f1 and this is f2. Okay. So, these are the two functions. So, the side way of representing this. So, these two terms are representing the first term f1. So, f1 is 1 1, other f2 is 0, and now for this 3 we are actually having the second output as 1 because this represents f2 and this representing is f1. So, now you see if we take these two x prime y prime z and x prime y z. So, actually this can be represented in terms of x prime means is 0, y prime cancels out and it is 1 0 1. So, this two represents is actually this one. Now, you can see if I take this two, that is x y prime z prime and then x y z prime. So, in this case you can eliminate these two, so it will be 1 dash 0. So, these two terms is represented by this one and both these terms are 1. Similarly, if you take these two, so if you take these two it will be generating this guy. Okay. Now, if you are taking the last two you will be generating this guy, and I think if you take x prime y prime z and x y prime z prime. So, in this case dash 0 0, sorry, if you take these two, if you take this middle two guys you will generate this term. So, middle two terms means x prime y prime z, no sorry. Okay. So, the 0 0 is generated by this two, 0 0 is generated by these two terms. Okay. So, first two terms, these two terms are generating 1, this is 1, these two terms, that is this term and this term is generating term number 2, okay, because x prime y prime z prime and x y z prime x x cancel out this one, and the last two terms, these two terms are generating the term number 3. So, and in all these cases you can see in terms 1 2 3 these last 3, this 3 corresponds to the f2 and this corresponds to f1. Okay. So, now this is now you can represent it in this way. Okay. So, I mean I did not go about in how do you represent this. So, in this case you can find out that 0 dash 1 is nothing but it is, you can say that this will represent this one, and this one is representing 1 dash 0 you can think is being represented by this one. So, this is how you represent the cover. So, this is your cover for f2 and this is your cover for f3. Okay. So, in this case you can think how many are there. Okay. This is 1 2. So, this 1 2 are here, and in this case it is 1 2 3 are there. So, but 4 are there, we will tell you how it happens. Okay. Now, in this case you see, so here you have the interesting thing you have to find out, that how you can go about minimization for this one. Okay. So, in the previous case what we have done, so we are trying to expand, I mean we are trying to take out some of the terms from this one, and we are trying to see if we can get some random covers, we were trying to take out one literal from this one, and then we find out if it still remains a valid solution and the cost is decreasing and so forth. So, in this case if you see, okay, so you will really find that we cannot do much over here. Okay. And in this case if you look at it, so what are the solutions we have to find out. Okay. So, we will see what happens. Yeah. So, in this case this value corresponds, this one corresponds to 0 0, no, just let us see what each of these things corresponds to. So, this is x. So, x is going both the way in this case. So, you can think that it is dash 0 0. So, this cube corresponds to dash 0 0 because x is moving from here to here. So, this one is corresponding, if you consider it 2. So, this is actually this number 2. Okay. Now, you can see this is dash 0 0 0 0 dash, that means in this case z is moving both the directions. Which direction is z? So, z you can find is top direction. So, in this case, so z is moving both the ways, but x and y are 0. So, this one actually corresponds to 0 0 dash. So, this corresponds to 1. So, if you see 1, this is actually the 1, because this is 0, x is 0, y is 0, but z is moving both the direction. So, this corresponds to term 1, and then we have term 3. Term 3 is 1 1, and it is actually x is moving both the sides. Okay. So, in this case you can think that this term is actually x is moving both the sides, but other terms are y and z are 1 1. So, this is dash 1 1. So, this is nothing but term number 3. So, we will see how this has come, how we will find out, I will tell you later how it has come up in this case. So, this one corresponds to this term dash 0 0, this is term 2. Okay. This one actually corresponds to 1, that is this one, and this term is corresponds to 3 in this case. But how this row comes, we will tell you later. So, assume that this term the question mark ellipse is not there, then how do you minimize this? So, in this case whatever I do, you can find out that there is no minimization possible, because if I remove this term, something like this, it will become this one, and you cannot, there is no way of merging it, because in this case if you look here, so we are having a very good way of merging it, because I mean here if this was there, we had done something to include this, so we could have eliminated this. So, in a very similar philosophy, you can just think over this, just assume that this guy's question mark is not there, and if you just look at this, there cannot be any minimization possible. So, that means if I mean you can make something like this, you can make something like this, but you cannot remove something and make a correlation between this point and this point. Diagonal connections are not there. I mean, how do you say about this? Say for example, it is 0 0 0 and this is a 0 0 1. So, how can you make a cluster between these two? Because 0 0 and this is the only difference, 0 0 1. So, this is 0 0 1 and this is 0 0 0, this point. So, one bit is different. So, you can actually make a cluster in between this. That means, you can eliminate one, literally if you eliminate, then this point will become this, like this. You eliminate some term from some literal from this one, it will make it. But you cannot have a merger in between the diagonal part, because merger in between the diagonal part means you have to eliminate maybe 2 or more literals. This is just like a consensus. In case of consensus, if you remember the tabular approach, so we compared sometime like x, y, z and x, y, z prime. So, we just compared in between these two, because there was one bit difference over here. Similarly, it is very analogous in this picture. So, that is if you try to eliminate something, so it will start making clusters in this way or in this way, but you cannot have a cluster in diagonally, because clusters in diagonal means, that means there are two terms which is different, like in this case it is 0 0 0 and in this case say it is x is 1 over here, z is, y is 0 over, sorry, x is 0 over here, y is 0 over here, z is 1 over here. So, you can see there are 2 bit difference between these 2 points. So, you cannot have a something like this. So, there is no minimization possible in this case. Similarly, if you just eliminate, if I do not think this one is there, so I mean if you do not, if this one does not exist, so same philosophy will hold. Now, what these people have done? These people have found out that these are different way of minimizing this one. So, what they have done? They have found out that these two terms are actually included in this. If we call it A and this we call it B. So, both of them are also available in function number 2. Okay, and but the 3 terms which is considering, I mean this 3.1 is this one, 2 is this one and 3 is this one. So, this middle, this guy is not present in F2, but it is present in 1. So, what they have done? They have said that, so initially if you consider F1, so this one will be this, okay, and if you and this term is also not available over here. So, if you just have a look at it, this is not there. But this 101, dash 01, if you make it a 1, okay, and add it over here, that is what is being done over here. Slightly different philosophy is there, 0 dash 1, and you can also think that it is a 1 and it will be still a valid solution. Now, why it is still a valid solution? Because you see this point is included over here and this point is included in the other, and so you can easily have it over here. So, they can say that and both of them are giving a 1 in both the cases, in both F1 and F2. So, they have just put this guy from here to here, and they have added, instead of having 1 0, if you remember in the case, they have made it 1 1. In other words, what they have done, they have made 0 dash 1 0 1, and in this case they have, and in this case it was this one, if you remember. Now, they have just made a club of it. So, in this case, if you make a club of it, you are going to get something like this. Okay. So, this is some different way of finding a different solution space. So, we are not exactly discussing the algorithm how it is done, because when it was single output, it was very simple, in which case we have to find out the nearby solutions and then we find which is the better one and so forth. But now, as there are 2 output functions, then you have to combine these 2 and see what better you can find out. So, in this case, you can see that this is the part which is common, because for these 2 points F1 is also 1 and these 2 points F2 is also 1. So, you take this one, you borrow it from here to here, that is what has been done. Okay. So, that is what is been written, that is there is no way this solution can be improved by expanding the inputs or the outputs, but if we expand the output of the first cube, this one, we obtain the cover as above. This is what we have done. So, you have exported it from here to here, and now you can go about for the solution. So, now what they have done? So, they have you can find out that if I put this one as extra, you have borrowed it from here to here. So, now you can find out that this one is a redundant cover, because this one is taking care of this point, okay, this guy is taking care of this point. So, obviously, this part will become a redundant point and it can be thrown off. So, this was actually considering, so this was considering point 1. So, that actually 0 0 0 dash. So, this is 0 0 dash, actually it was considering this cone which can now be removed. So, now it is represented in terms of 4 terms 1 2 3 4, and so a reduction has been possible. Okay. So, what I am saying is that, so what I just want to emphasize is that, so more the number of outputs, or whenever you move from single output to multiple output cases, the searching the neighboring solutions become a more sophisticated procedure. In the previous case, single cover, what was the next solution? The next solution was just eliminating one of the literal and you could find the neighboring solution and keep on doing it. But if you have multiple output functions, the things are not very simple. Okay, so this is one function and this is two functions, there is two output functions. So, now in a two output function, obviously this circuit is going to, if a circuit has two outputs, so some logic gates are shared by both the outputs. So, that philosophy has to be brought into picture. So, finding a neighboring solution here may not resort to just like removing one literal and finding out a solution. So, if you just think about this, because in this case this will not be there. So, I think this was your some 1 2 3 is there. So, these things only correspond to some of your terms. So, this dash 1 1, this is dash 0 0, something like this. This one is not there. So, and these things are there, but now you can think that for these two and these two, both of the functions are 1. So, you borrowed this guy from here to here, and then you can say that this one becomes a redundant cover and remove it, and you can get a better solution. But there is no elimination over here, this more or less remains same. Here there is no optimization, only in terms of F2 there is an optimization. So, for finding the neighboring solution in this case, it was not just about removing one literal and doing, but rather doing some export and import from each other. So, that is what is being done. So, it is being moved from here and here, and then you can remove this as the cover. Here it remains same as the old solution, that is these two will be there, but we could have saved something in the F2 business. So, what apart I am saying that we are not exactly telling how we have got this. I mean, in case of single output, the answer was remove some literal and see what is happening and what is not happening. But in the case of multiple output, we have to take some solution from point function A to function 2 and solve about it. So, therefore, what I am emphasizing is that in case the heuristics by local search is very simple. Take a random solution, finding a neighboring solution, see if the cost is good, keep it, else reject it and keep on doing it. But moving from solution space 1 to solution space 2 is a very difficult problem, because heuristics, otherwise heuristic design would have been a layman's job. That is, you take a solution, take another random solution, if it is good keep it, else remove it and keep on doing it. But finding the next better solution is where how your algorithm time will be considered. So, if you take n number, if you think that I want to take a next random solution, and the way your next random solution will be taken is totally arbitrary, and you do not pay any attention to that algorithm which is finding out the next random solution. So, if you keep on try just searching in the random solution without any hint, and then you may try to land up, you will take a very long time to get to a good solution. But if your algorithm is good, then from the current solution to the next solution you go, you think a little bit and then you go to the next solution. Like in the case of multiple output function, it was not as simple as removing a literal, it is something you think about by merging something and so forth and importing some of the terms from output 1 to output 2 to get the next solution. That is, the next solution you are selecting intelligently, then your search will be quick and quickly you may go to a optimal solution. This is very similar, like say you are in a forest and you are trying to track some animal to shoot down. Okay, so like for example, in case of poacher. Now, if it's a, if the hunter or if he is an intelligent person, then what he will do? He will try to hear the steps of the animal it is targeting. Then he may try to look at the what you call the footprints of that, and then to try to find his way. He is also not directly does not know the point where the animal is. He is also trying to look for the animal in a heuristic manner. Just but by looking his experience, he is trying to find out which way he should go. If he find out the foot imprint of the animal, then he will try to go in this way. But the person who is totally unexperienced or unexperienced hunter, so what it will do? He will first try to run 10 meters, maybe say in one direction, then he may try to run in another random direction in 10 meters. So, for him finding the animal will be a very long process. But for the intelligent person who is just taking some hints, that is to find out his next course of action, he is paying lot of intelligence, so he can get to the optimal solution very quickly. So, that is about heuristics also. Current solution may be random, but finding out the next solution you are going to try out is a very intelligent problem, that you have to find out how among all the neighboring places which one you should target next and see its quality. So, this is how it goes about. Okay. So, now so in the examples last section, last class we suggested the procedure based only on the simple moves that immediately the cost decrease is effective. So, what it is saying in the examples in last section, the procedure was we actually remove some of the literals or import or export something, and wherever the cost decrease is effective, that if the cost decrease you keep it and keep on repeating it. But in a real scenario, we may need to consist a wide variety of moves and combine them into a sequence of moves that eventually lead to the desired result in reducing cost. Otherwise, we need to consider moves that may not immediately reduce the cost. This is actually a very difficult problem. That is, as I told you, this is the case. So, if you are always thinking that the next solution will be my best solution, I will keep it, then you may get stuck up into a local minima, because you are always coming down. But sometimes if you find out that this solution is something like this, here you may get a better solution. So, sometimes you have to also take the bad solution and you have to jump up, that is what he is saying. In other words, we may also need to consider moves that may not immediately reduce the cost, but that is a more difficult problem to solve. Okay, now we are going to see the simple local search algorithm for logic minimization in the Espresso. Okay, so now what in the previous part we have done? In the previous part we have taken what you call this what you can say the prime implicant form. So, you can say that we started with this prime implicant form of a stuff, and then we are trying to remove some literal and something and try to go for the next best solution and so forth. But now in case of Espresso, as I am telling from the very beginning of the lecture, that is the main emphasis in this lecture is Espresso. Here we will not go about any form of min terms or merging or something like this. We will rather take the SOP form directly and apply the rules and keep on applying it till we get a solution of our desired value. That is, we will never modify the solution to get the set of prime implicants, because that is what is a complex problem. Finding a prime implicant is a problem, then finding a subset of them is another complex problem. So, here what we will do, we start off with this SOP formula as given as to us, and then we keep on modifying it in some means, like in this case we modified by removing one literal. Okay, same thing we can also try to do it by modifying by removing some literal, adding some literal and so forth. So, taking a literal out, adding a literal out is actually searching the neighbors. So, this heuristic for logic minimization Espresso has its own way of searching the neighbor space. So, that we are going to see, but again emphasizing here we are not starting with any kind of prime implicants. So, it has very basic 4 steps. First step is expand. Okay, this step expands the implicants to their maximal size. Okay, implications considered are by an expanded implicants are removed from their consideration. I will tell you what does it mean. Quality of results depends on the order of implicant expansion. Heuristic manner are determine the order. So, what it says, this step expands implicants to their maximum size. That is, say for example, you have x y, okay, and it is a function of z. So, you can expand it x y z prime plus x y z. So, actually you try to expand, but you do not expand wholly. You take one literal at a time, like x, y, z, whatever one, and you expand the functions as much as possible. But in canonical representation, what we do, you have to expand all the terms in all possible literals. If you have the function of x, y, z, you have to represent all the mean terms, that is, after expanding all the terms of the SOP in terms of all the literals. But here you select one of them and you expand fully. Okay, then with the maximum size, implicants covered by expanded implicants are removed from further consideration. Obviously, if you have a implicant which is being covered by some other, you can eliminate it. Now, the results will depend on the order of implicant expansion. Like for example, if you should you start with x or y or z or a or b or whatever. So, that is what again very important in heuristic is that you are searching the next solution space. In this case, next solution space is you are selecting a literal like x, y, z or whatever by which you are expanding. So, if should you start with x, should you start with y or so forth. So, depending on which one you try with next, it will actually give you the how fast you are reaching your solution, that will be determined by it. This is just like the example of a forest and a hunter I have given you. Which direction you should proceed next will also be very critical in finding out the time criticality of getting to the good solution. So, in this case there are also a lot of algorithms or heuristic algorithms which will tell you which, based on the previous results, which literal you should start expanding with. Then that is redundant cover. Redundant cover is no proper subset is also a cover, is expanded from the expanded set of primes. So, we will see when we will come by the expansion. So, redundant cover, there is no proper subset is a cover, that is, if you have some redundant terms you can eliminate it, okay, reduce. So, in this case what do you do? There might exist another cover with fewer terms or literals, seek prime implicants to the smallest size till it cover the mean terms. So, do not consider these lines, okay. So, we will see what does that mean. So, here we are not at all bothered with any types of primes over here. What we do is that we this step expand the implicants to the maximum size, then irredundant cover, that is, if you have some terms which are redundant, it becomes redundant, we can eliminate that, and reduce means there may exist another cover with a fewer terms or literals, that means now you are again going to shrink it. Okay, so and then you repeat this procedures, reduce, expand, independent cover to find the alternatives. You keep on doing it till you get the solution. So rather than rightly explaining these steps, I will give you an example, and again I will come back to this slide. See, this is a function, say. Okay, so this is a function. These are the mean terms. Okay, so now this just mean terms are listed. Okay, just for example, but Espresso will not be actually involving anything about this. What it will do? Say for example, this is a function f is written in terms of a prime c prime plus c prime d plus ac plus something is written over there. I do not bother whether they are mean terms, whether for their prime implicants or whether they are essential prime implicants or what. Some form is given to this one, and this actually represents this, but Espresso will not also bother about what it represents. So just see, this is what is the case. So if you just look at it, what will be this one? This is nothing but a prime c prime, okay, and this box is nothing but what you can say c prime d, okay, and this one will be corresponding to ac, okay, and this one is corresponding to CD prime, correct. So this is how is represented in a Carnot map. So Espresso also do not think about Carnot map. For it, this one is the only thing that is matters for it. Okay, so this is just like this is just a given term for this one. Okay, this is just given to you just for pictorial representation. I am showing the Carnot map. Again repeating, this is only what is important to Espresso. Espresso does not think what are a prime, c prime, prime implicates. It bothers nothing about it. It is given to you. Okay, so again I am playing this is a very simplified version of Espresso. If you go for the advanced version or the implemented version of Espresso, there are slight changes or some changes over there. Okay, so as the scope of the course is limited, so we are just discussing the basic idea of Espresso. So this is given to you. Next, what did you do? Now we reduce. Okay, so what did it say? Reduce. Okay, so expand, redundant, cover. So these are some of the steps. So first step is reduce, then you expand, then go for the redundant cover. Reduce, expand, redundant cover. So this one you do about with. Okay. So now what you do? So now you have to see this one is there. Now we have to reduce. Okay. However, keeping in mind that all the mean terms are covered. Obviously, the mean terms are covered. That means when you have to reduce means you are actually shrinking it. Okay. So in this case you have to shrink it. Reduce means we will be shrinking. That in this case we will try to put in some more variable. I will tell you what does it mean. What does reduce means over here. So reduce means shrinking. So in this case we will shrink it, and obviously you have to also think that always you have to be sure that the function is equivalent. That is whatever was covered in the previous version of the solution should also be, mean term should also be covered in this case. So now what is this? We use a for making the reduction. So a for making the reduction means you are actually, so in this case if you remember the old part, so this was your actually the solution, this one your solution, and this was nothing but c d prime. So you are expanding by a means, so this was actually nothing but c prime d, right? Yeah, this was c prime d. This was c prime d. Now you expand with a, that means what? Sorry, you are reducing with a, that means you are using a to cut it off. So in this case what it will become? You just put it as a. So it will represent as a c prime. Okay, so now c prime d, see this one. Initially, if you look at the initial solution, it is a c prime, c prime d, a c and c d. So you just break this term. So that is what is reduced, means you are breaking the terms in terms of one literal. So you are putting one literal explicitly in this. So in this case, you are putting one literal a in this case. So in the last example, next solution was removing a literal. So in this case, we are adding a literal. So that is the first step of this. Once you are adding a literal, so it is actually breaking it up. So adding a literal means it will break this up. So now only this one will be remaining your term. So it will be nothing like, it will be a, then it will be it will be c prime d, c prime d. So in this term you are adding one more term. So you see the function is now becoming something like this. It is a c prime, okay, a c prime d, a c, and there was another term, okay, a c prime d. There was another term over here, a c, okay. That is the case, and c prime d was there. So now again there was another term, if you have a look at it. So this was another term in which a was involved. So this was another term in which a was involved. So that also you have to break it up. So if you break it up, what is going to happen is you are going to get this term. So this term is nothing but a prime c d prime. So this is another term which is coming out. Initially you had a term something like this. Now what we are doing, we are selecting the variable or literal a and we are breaking the terms. So there is by this term was continuous, so this one will get broken. This was another term which will also get broken. So obviously these two terms cannot, this term cannot be broken and this term cannot be broken because they are already inside a. So now this is what we are getting is the final picture. So now this whole equation, this variable and this term has now changed from this one. If you look at it, a has been inserted over here, and also in this case some a has been a prime c d prime. So here it is one term and so one term added over here, right. So this is how you have broken up these terms. So this is called the reduction. So in reduction, what you have done? In reduction, you select the term like select a literal and you break up this term. So in this case, these terms have been broken. So it was initially the whole stuff was there, you break it up. This was all was there, you break it up. So you have broken this. Next, what you do is expand. So now expansion, what you do? You take another variable and start expanding. So in this case, I will tell you what is there. So let us say another term, in which case, so we expand with literal c. Now you are expanding with literal c. So in this case, if you see, so in this case was there. So let us try to expand this. So the expansion will be something like this, and this expansion will be something like this. Now why is it so? Okay, so now we expand a c prime d. So this was actually, let us look at this. So this was, if you just have a look at this one, so this was nothing but it was a c prime and d. Okay, so this was this value, this small value, these two terms were there. If you just have a look at it, this one. Okay, so now we are expanding in terms of c, and also you have to be careful whether it is possible. In this case, it is possible because this now if you expand with c, that means what? It will become something like this, and it will be nothing but AD. Well, now this is possible because these two guys are also a part of the min terms. Okay, that means these two also comes in the terms of cover. But had it been the case that these two terms were not there, then if you want to expand by c, then it will become an invalid solution. In this case, the valid solution. So therefore, it is possible. Now you have expanded in this fashion. Similarly, this also can be expanded by c. Now why it can be expanded by c? Because these two are also in the cover. So you can expand it by c. So what it will become, if you extend it by c, it will become c d prime. So this one is again c d prime. Now, so this is your final case. So now similarly, a c prime d is using the literal, so it is a, so it will becoming c d prime. Okay, so you are expanding this one, and a c d prime using literal a. So now you are expanding this one by a, so you are getting this value. Okay, now so this is your formula. So now what you can see over here. Okay, so there are two expansions over here, that is very important. So this one you have expanded by c. So this you have expanded by c, this one. Now if you say that this one also I want to expand by c. This one I want to expand by c means what? It will actually become this one. So in it, now this is what? So if you just look at this, so this one was what? This one is nothing but your a prime, c and d prime, something like this. Now if I want to say that I want to expand this by c, so by c, that means it will become something like this. So c will be gone. So it will be nothing but a prime, it will be a prime and yeah. So if I make it this way, so it will be a prime c. Sorry, it will be a prime. It will be a prime c if I go it in this way. So okay, if I want to, sorry, you can do this. So if I want to expand it in, so I have done an expansion in this way. Okay, so forget about the other ways which I want to expand in this way. So if you want to do it by this manner. So in this case, I see it becomes AD. So AC prime you are expanding by literal C. So it comes over here. Okay, now this small term in this case was, sorry, this case was AC prime, or sorry, this was A prime, C and D prime, right. Now if you want to expand it by C, so it will become A prime, D prime. So if I just want to expand this term by C, okay, just eliminating C. So what it will represent? A prime and D prime. So A prime and D prime means it will be this term and it will be these two terms. So it just this two term now is actually A prime, C prime, A prime, C and D primes, these two terms. Now if I say that I want to expand it by C, because this one I have expanded by C. So this term was nothing but A, C prime, D. So just eliminating C prime by expanding by C, I actually got over this, and this is nothing but your AD. Okay, that is possible because these two ones are a part of the cover. But now, and this stuff actually is A, C prime and D. So if I want to eliminate C from this one, that is expand by C, that is I remove this, that means it will become A prime and D prime. A prime and D prime are nothing but this and this. So you can also think in this manner. So in this case, your solution will look like something like this. So you will have stuff like this, you will have a stuff like this, and but here you can see that I cannot do anything much over here. So this term will be there, this term will be there, this term will be there, and this term will be there. So cost will be same. So what these people have done, they have taken another way. So they have said that this I do it by C, that is no problem. So in this case you are actually getting a expansion over this one, that is expanded by C. Okay, so you are getting this one, you expand by C, you get AD. Now we have seen that if you expand this term by C, you are going to get something like this, and there is no minimization possible. So now what they are doing, the second term, this one, they are expanding with terms of literal A. Okay, so if you remove literal A, it will become CD. CD prime. So, okay, so this is, that is, you are not expanding it in terms of C, this term, they are again expanding in terms of an A. So if you are doing it in this way, so what you are getting CD prime, that is nothing but this one. So finally you are getting this. So okay, so finally you are actually, this is the case your expansion. Now you can see that you are getting a redundant cover. So that is this part, this inner square is redundant because everything is covered. So you can eliminate this, and now you can have this, this, and this, and you have got a minimized result. Okay, so that is what is an espresso. So let me again reiterate what I have done. So what is the first case? First case is reduce. So what do you mean by reduce? Reduce means there might exist another cover with a fewer literals. So shrink it. So do not think about any prime implicants in this case, because shrink prime implicants to the smallest size that cover the mean terms. So in this case that is the resultant. So in this case what will happen, if you keep on reducing, so finally you will have prime implicants in the end that will actually cover all the mean terms. That is what is going to be, you are going to get it. But espresso does not think about it, it first reduces it. That means what it will do, it will actually try breaking the terms with fewer number of literals. That is what is actually reduction. So what it is doing, so let us just see. So what it has done, reduce. So in this case initially we had this solution was this one. So initially we had this solution is this one. Okay, so what this first is a reduce. Reduce means you are breaking it. So this time he has broken up and this time he has broken up, and he has chosen A to do it. So just breaking this one with, it will be CDA prime and it will be A CD prime kind of a thing. So you are going to get something like this. So that is what is being sold. For reduction the cover as this one is one term added and this one is one term added. Okay, so this is changed to something like this. So these are the two things which are generated by reducing the whole thing by A. Okay, now we reduce the covers. Now what you do? Now you again go for an expansion. So what is the idea? It was reduce, expand. So once you have reduced it, now you have to expand. So by expansion can be again in terms of this one. So in this case, so they have expanded in terms of there was if you look at it, so this term they have expanded in terms of C. So by C, so if you expand it by C, you will get it over here, and if you expand this by C, you are going to get something like this. But again, expanding both by C have not led us any advantage, because you require 1, 2, 3, 4 terms. Okay, now they have again started forgetting that they have started expanding this one by C, fine, but this one by A. If you expand this by A, you are going to get something like this, which is nothing but this term, this figure. Okay. Now if you do this, then you find out that this guy is now it becomes redundant. So that is what is being said, that reduce, expand and redundant cover. This redundant cover, that is no proper subset is also a cover. So in this case this is a subset. So this becomes a subset. This one is your subset, sorry. This one is also a subset, that means this is a redundant one. So the smaller box, this can be eliminated and you get something like this. So, and which is actually in this case is optimal solution, but now you have to keep on doing it. You can also try, first we have tried with breaking up with A, then we have merged with C and A, then again we can start with B, and you have to keep on doing it till you get the desired solution or this one. Okay, that is what is espresso. Now again in a nutshell what espresso does, you first given any SOP form, you take it as it is. Now what you do, you start reducing. That means you start breaking off some of the terms, that you are breaking it up. Okay, now what you do, now you expand. So now you expand in a different directions. Now you again, once the expansion is done, you find out if there is a redundant cover. If there is a redundant cover eliminated, then your terms have obviously solutions become less and you keep on doing it. So if you have to just observe that this is what exactly is being done in case of prime minimization as a human being does in case of Karnaugh map. So what it will do, he will first make some clusters, like for example he may first make a cluster like this, he may make the term like this, he may join like this, he may join like this, and he may join like this. Then he may think for a while, saying that Okay, well, let us try to actually try some other solution, in which case he may say that okay, this is all solution, that is let me try out other way. So, he may have broken up this one, that is he is trying to cut some of the things and expand in another direction, that is cutting in one direction, adding in one direction. So, he just cut this off and then he started making a club like this and making a club like this, and then find out that this can be eliminated. So, espresso works in a very similar fashion as a human being does. So, it actually first cuts off some of the terms already present, and then it actually expands in some other directions and see if something can be eliminated, and it will keep on doing it till this solution actually reduces. So, this is how, is a very, in a very broad sense, how espresso works. And how the complexity is reduced, because you do not have to think about which are the prime implicants, what are the mean terms, etc. Nothing you have to do. Given some expression form is there, you take one alpha, you take one literal and you expand it. Now, you take another literal and you you add one literal to some all the terms, so that it gets reduced. Now, what you do, you take out some other literal, so that it gets expanded, and you find out the redundant cover. Redundant cover means some of the whole cubes can be removed. If the terms become less, it is good, and you keep on repeating it, you get the best solution. So, this is overall the most widely accepted heuristic in the VLSI area. I mean, design area, if you ask me what is the best heuristic possible that has been developed, that is nothing but your espresso, and all logic minimization are standing in the feet of espresso. So, but this is a very simplified version I have told you. Expanded version or intelligent version of espresso, what they will do, I mean, or the which is implemented will tell you which is the first literal to start to reduce, which is the next literal to expand, and so forth. So, choice of the literals are very important, and will be told by the algorithm. Okay, so, this is about the heuristics, minimal search, optimality results, optimum results, and finally, the algorithm espresso, which solves all the Boolean function minimizations in the modern CAD industry. But this was a very miniature or very small version, or simply very simplified version of heuristic, which I put towards you. Now, I mean, let us come to the question answer session. The question is, why simple logic search algorithm for logic minimization is called an algorithm? Why do I tell you that espresso is an anytime algorithm? So, what do you mean by anytime algorithm? That means end of each solution or end of each iteration is a solution. That is another very important point of heuristic. So, you just run espresso for one round. So, one round what you will do? You will reduce, you will expand, go for redundant cover, and a solution is there. You can use this solution. Again you go for another round, another solution will be there, and it is ready. So, at every iteration some solution is there. That cost may be very high. More down the line you go, slowly the cost will start reducing. But at every point of time, all the mean terms or whatever solution you have, that is the cubes, will actually cover the function. So, at any point you can stop your heuristic, and you can, whatever cubes you have, they will cover your function, that is guaranteed, and that is a solution. Therefore, it is called an anytime algorithm, that at every iteration you are going to have a solution. So, that is another very important point of espresso. That is, I mean, you never have to let the algorithm stop for the given a stopping criteria or whatever you say, but at every point you are going to get a solution for this one. That is why it is called a anytime algorithm. But more time you give, the better the solution will be. Okay, so with this we come to this closure of this lecture. In the next lecture we will see how to minimize sequential circuits, because this was all about combinational circuits. So, next time we will see that how to go about minimizing implementation for sequential circuits. Thank you.